Okay, let's explain the statement. So I'm given a tree consisting of n nodes, and of course n minus 1 edges, and I want to distribute integers on each edge of the n minus 1 edges in such a way that satisfies the following three conditions. Okay, so each integer must be greater than 0. The product of all the n minus 1 integers should be equals to k, and the number of ones among all of these integers must be minimum possible. Okay, and then define f of u of j as the sum of the numbers on the simple path from node u to node v. And I want to calculate, so this formula means I want to calculate the summation of all the summation of f of u of v for all pairs of u and v. Okay, so I want to calculate the summation of the numbers of every path on this tree. So we have n choose two paths. So we have n choose two pairs of nodes in this tree, and I want to calculate the summation of all the numbers on these n choose two paths. That's it. And this value is called here in this problem a distribution index of the tree. We want to find the maximum possible distribution index we can get, and then print it modulo 10 power 9 plus 7. Okay, that's the explanation of the statement. So let's say things again. So we have a tree, and we will distribute numbers on this tree, but we want to distribute these numbers on the tree in such a way. So we will distribute this number in such a way such that the distribution index of the tree is the maximum possible. Okay, that's it. And since can be very large, we are given the prime factorization of k. So we are given up to 6 times 10 power 4 prime factors of k. So p1, p2 until p of m. And we will distribute. So what does these three conditions means is that we will only distribute these factors in the edges, and if the number of these factors is smaller than n minus 1, then we'll continue with ones, right? But we want to make ones small as possible, so we will we will distribute all the factors of k on the n minus 1 edges, and then the remaining parts that doesn't have any numbers we'll put ones. Okay, but what if the numbers are the factors are greater than k? We will are greater than n minus 1. We will see that. Okay, but let's first forget about the to make things easier, forget about the k now, and forget about these conditions, and let the integer at each edge equals to 1. Okay, so let's see how can you calculate f of u of v for each pair of u and v if the integer at each edge is 1. Okay, of course, while I'm explaining now, if anybody have any idea, just cut me and say it to be good. Okay, so let's say we have some graph here. We have some tree here, sorry. Okay, so this is a tree, and let's say that the number on each edge is 1. Okay, or actually let's say, mm, okay, the numbers are 1. So how to calculate distribution index of this tree? So an easy way, so the easier way, but this would require much time, is to loop through every pair of u and v. So hold one and then go to every other node and then check one with two, one with three, one with four, and so on until we finished checking one with every other node, and then check two with three, two with four. So check every pair, and after checking every pair, we do DFS to check the distance between this node and the other node. Okay, so if this is 1, this is 4, and I want to check the distance between 1 and 4. Then I do DFS from 1 until I reach 4, and then the distance will be 2. Then I'll do this for every pair, but the complexity of this algorithm would be of n power 3, so it will be n cubed. So this is not good. We could make it straightforward to O of n. We could make this way better, and we could only calculate the distribution index of any tree in only O of n. But how could we make that? So realize that um, we only care about the value of each edge. We don't care about any pair, because so to calculate the distribution index, we just, if you have some number of edges, n minus 1 edges, we just want to know if this edge, what are the number of paths that contains this edge. So for example, if this edge is contained in 4 paths, and this edge is contained in 3 paths, this edge is contained in 2 paths, this is 3, 3, 3. So we have this edge is contained in 4 paths. So for example, let's take a realistic way here. So let's take this edge, okay? And if I would count the number of paths that contain this edge, so it would be, here is one path, here is another path, here is another path, another path, another path. Can you see my pointer here? Yes, you see my pointer. Okay, so one path, one path. So many paths. Okay, so if I want to count down the distribution index, I'll just add I multiply one by the number of times each edge is contained in a path. So the distribution index for this, for example, would be 4. So it's not really, I'm outputting any numbers, okay? So it will be here 4 plus 3 plus 2 plus 3 plus 3 plus 3, okay? Because this edge is contained 4 times. So I'll add the value of this edge 4 times in the distribution index, and then add the value of this other edge 3 times, 2 times, 3 times, okay? So here, let's say the values of each edge are not 1. They are anything, 3, 4, 10, 7. So these are the values that are put on the edges, okay? 8, 2, 2. So again, to calculate the distribution index for every edge, we will just, it will just be, for, let's start from this index, it will just be 3 times the number of paths that contains this edge, okay? So let's say this is I. So it will be 3 times I, let's say paths of 1, plus 4 times paths of 2. So let's say the index of this edge is 1, this is 2, and so on. And then plus 10 times paths of 3, and so on. So actually, it turns out that we can get the distribution index for any tree by just counting the number of paths that contain every edge. That's it, and then multiply uh, this number of paths times the value on this edge, and now we got the contribution. So this problem known as something like contribution problem. So this way we know the contribution of each edge in the tree, and then multiply this contribution by the value on this edge. So that's it. So that now that we know how we can calculate the distribution index for any given tree, but this is not the problem. We want now to distribute numbers in such a way to maximize this distribution index. Okay. So let's again forget about the numbers now, and let's get the paths, the number of paths that contain every edge. Let's go from drawing now. And now we calculate in some way, somehow, we'll see now how can we calculate the number of paths that contain every edge. But now we have n minus 1 edges, right? So edges, and I have n minus 1 edges. And for each edge, we will store the number of paths that contain this edge in an array called paths. Okay, so paths should be of size n, and paths of I equals, so paths of I should be equals to the number of paths that contain the ith edge. Paths that contain the ith edge. Okay. So now that we have some number of we have some array paths. Let's say it's 2, 5, 7, 4. We want to store it. Okay, we will store it. So we want to store it. Maybe 15, 20. We want to sort it in an increasing way. So we will sort paths. We will sort the array paths in an increasing order. It may have duplicates, of course. So now we have some n. So here for this is for n equals to 8. This is for n equals to 8. So we have n minus 1 edges. So here is some edge that's contributed in 2 paths, and another edge 5 paths, 7 paths, 10 paths, 20 paths, another 20 paths, another 30 paths. Okay, and we will have another values that are put in the tree. So let's say that are put in each edge. So value of n. So let's say the values are something like this. We will also sort them. Okay. So now that we have the values of each edge, and so now let's say that we know now what values will be put in the tree and in what way. Okay. So as we said yesterday, so the best way to get the value. So before that, so to calculate the number, so to calculate the distribution index of this, it will be just 2 times 4 plus 5 times 5 plus 10 times 8. So it will be each edge multiplied by, so the contribution of each edge multiplied by the value put on it. Okay, so that's it. But the best way to make that is to multiply the greatest with the greatest, as we proved that yesterday. So multiply the greatest with the greatest, and the second greatest with the second greatest, and so on. So this is the best. So the best value we can get out of some numbers that are put on edges is after sorting the two arrays. Okay. Okay. So now what is only left? So we will see now how can we calculate the number of paths for each edge. So this first array is good. We have this. What's only left is how to get these numbers. So we said that we will be given some prime numbers and we want to distribute these prime numbers on the edges in such a way to minimize the number of ones. Okay. So we'll be given some array called P. And it will be of size M. So we have two cases, or actually three cases. If M if M is smaller than n minus 1, so M is smaller than the number of edges, then we'll just distribute all the prime numbers in a way that we said to maximize the answer, and then the left will be ones. Okay. So let's say we have P equals to 5, 6, 7, 8. That's it, 4 values, but n minus 1 is 7, so we'll add the left 3 values of 1. Okay, that's it, and then we'll calculate the same way as I said. We'll multiply the greatest with the greatest, second greatest, and so on. But what if m is greater than n minus 1? So if m is greater than n minus 1, then we will have extra values. Actually, each number here should be prime, so we cannot have 8. It should be 13, 11, let's say anything. Okay, 17, 19, 23, 29, 3, 4, 5, 6, 7, 8, 9. So now we have 7 values in the array of paths, and we have 9 values in the 9 values in the array of P. Okay, so we have an extra prime numbers. So let's see what's the best strategy here to distribute these prime numbers. So these we have extra 2 prime numbers. So we should actually multiply some number by another number to mix them into one, right? Because we want the product of all n minus 1 numbers to be equals to k. So if we multiply it, for example, 2 by 29, and then put it in the same spot at the same edge, so we decreased the m by 1, right? And then if we multiply it, for example, 5 by 7, so we now have an okay array with equal size, right? So we just want to multiply two numbers. We will multiply two numbers. We will be multiplying every two numbers until m is exactly equals to n minus 1. But what's the best two numbers to multiply to achieve the higher score? So it turns out that the best numbers to multiply to achieve the higher score is the greatest numbers. So let's say you have another x, another y, we have many numbers. So we'll just multiply all these 4 numbers with each other and then multiply it by this number to make it all with the same size. Okay, so we'll have a new array here with 23 times 29 times x times y times 19. Why is that? Because I said it's better to multiply the greatest by the greatest. And here we will increase the greatest value as much as possible to multiply it by the greatest value in the paths array. So this will give us the best value. Okay, but if I, for example, multiplied 2 by 5, so if I took from the least values, multiplied 2 by 5, then I'll just get a multiplication of a smaller value here from the paths array. So this is not good. Okay. So that's it. That's how how we distribute the numbers. So again, uh, we don't we don't put the numbers in the tree uh, as the problem says. We just store them in a way that maximizes the distribution index. Okay. So any questions before I jump to code? Any questions on the idea? Anything you are not sure about how I got it? Please ask if you have any question. Okay. I feel like there are many questions, but you don't want to ask. Let's jump to code. So before coding, the first part we want to know is how to calculate the number of paths that contain each edge. Let's go to drawing here. Let's say we are standing at one edge, at some edge here. Okay. Okay, so here we are standing at some edge and we don't care about these other edges. What we care is we want to put some number here that's the number of paths that contain this edge. How can we get that? So it could actually easily be get by getting the number of edges at the right side and the number of edges at no, not number of edges, the number of nodes at the right side and the number of nodes at the left side, and multiplying them together. So here we will have left nodes equals x. Oh. Right nodes equals to y. So we will again somehow count. So to calculate the number of paths that contain this edge, we will have a pre-stored number of nodes that we can get very quickly from the left side and from the right side. Okay, so let's imagine now we have the number of nodes at the left side. So this is a tree. So we have nodes here at the left side and nodes here at the right side. So if we multiply the x by y, we get the number of paths that contain this edge. Why? Because actually this is every pair of paths that path through this edge. So if I have some node here, some node here, so 3 nodes here, and here 2 nodes, for example. So I multiply just, so if all the numbers I have here is 3 nodes and here are 2 nodes, then I'll multiply 2 by 3, then I'll have here 6 paths that path through this edge, right? Because I could have okay, this is 9, so I have 3 times 3, so 3 nodes times 3 nodes, because I could go from this node to this node, or this node to this node, this node to this node. So I could go from every node on the left side to every node on the right side, passing through exactly this edge, right? So just to get the number of paths that contain this edge, we will multiply x times y. That's it. So xy is the number of paths that path through this edge, right? Let's see now how can we calculate the number of nodes in the left side and the number of nodes in the right side. We'll draw another drawing here. But here's a normal tree. Starts at node 1. Okay. So let's say you are standing at this edge right here. So let's say you are standing at this edge right here. So we said that we want to cal to calculate the number of nodes at the right side and the left side, which is here down and up. So here is the right side. I want to calculate the number of nodes at this right side and the number of nodes at the left side. Okay. So I multiply all of these by all of these. But how to get the number of these? It turns out that we could pre-process it in an easy way, and I'll say it now. We will start from the upper node, and then with with a normal DFS, I'll get the number of nodes below this node. So from one, so paths, so nodes of one will be equals to number of nodes below one plus one, of course, because number of nodes below one plus one is which is the current node itself. Okay, and then for every other node I go, I'll count. I'll put nodes of I equals to I plus the number of nodes below I, right? So here to get, for this edge, to get the the number of nodes below it and above it, after doing that DFS and storing nodes of this, storing nodes of X, we will get the number of edge by saying nodes of X, which will store the number of nodes below X and containing X. It will be multiplied by the upper nodes, and the upper nodes could be get by just nodes of one. So nodes of one is clearly all the number of nodes minus sorry for that, I was talking to someone. So nodes of X times nodes of one multiplied, actually subtracted from nodes of X. Why is that? So nodes of one have each and every node, and nodes of X are these three nodes. So if I subtracted nodes of X from nodes of one, I get the upper nodes. So I'll just multiply the upper nodes by the lower nodes in this way. Okay? Did you all get it? So nodes of X multiplied by nodes of one minus nodes of X. So how can we actually calculate nodes of
Ahmad,
every
I have a doubt on this. For nodes of 1 equals number of nodes below 1 plus 1, the formula over there is, why is that plus 1?
So plus one is containing one. So nodes of one means the number of nodes below one plus the current node, which is one, right? So
Okay, then if you come to the below node, it will be the same formula, right?
yes, yes.
So then anyway, that node was counted on the above 1, and again you are adding 1, so that will be a duplicate, right?
Sorry, can you say that again?
Okay, for example, the node 1 will have all the below nodes plus 1, so that is fine. Then if you come to the below node, for that node, yeah, so that one will also be all the number of nodes below that plus 1. If you're
Yep.
adding plus 1, that node was already counted on the above one, right?
No, I calculated from the beginning. So uh, so nodes two will be equals to the number of nodes below two, not below one, plus one. So it will be So it will be these nodes plus 1, right? So nodes of 2, uh, sorry, I did something wrong here. So this is 2. So nodes of 2 will be equals to the number of nodes below 2 plus 1. So there is no duplicates here. And nodes of 1 will be equals to nodes of 2 plus 1. And if I reached a leaf, so this will make it easier. If I reached a leaf, which is,
Mhm.
so the number of nodes below this leaf is 0, right? So
Yes. Yeah.
nodes of any leaf will be 0 plus 1. So here 0 plus 1, so it will be 1, 1, 1, 1. So here will be 1, 1, 1, 1, 1. And for
Okay.
this node, I'll store 2. And for this node, I store 1 plus 1 plus 1 plus 1 plus 1 plus 2 plus 1. That's it. Did you get it
Okay.
now?
Okay. Okay. I got it. Thank you.
Okay. So let's calculate now nodes. Let's see what are maximum. Okay. So let's do a DFS to calculate. Let's call it calc, and to have current node and the parent to traverse the graph. So okay, so for this DFS, we'll go from the upper node and then go to the lower nodes. Okay, so the value of the current node will just be, we'll just set it to 1 for now, which corresponds to this current node. Okay, and then after setting it to 1, I'll add to it the values of nodes of the children of it. Okay, so that's it. So for child, let's make an adjacency list here to store edges. So now we are standing at each child of node. We will add two nodes. So let's say what should the function returns. So the function calc of node of parent should return the value of nodes of node. Okay, so at the end, after calculating everything, it should return nodes of node. So it calc of node should return the value of nodes below node plus 1. So to get the value of node, we'll just add to node of node. I'll just add calc of each child. Did you get that? But first, I want to check that this child is not my parent, because they are all connected to one edge. So child not equals to parent. So that's it. That's how calculate nodes, uh, nodes of node for every node. So let's say that again. So we'll first put one to nodes of node, and then we will add to the value of nodes of node, we will add the values of each child, okay? And for each child, I'm returning the value of nodes of node. So at the end, it will get uh, nodes of node will be equals to exactly the number of nodes below it plus 1, okay? Any questions here? Okay, let's jump to the input now. So we are taking t-test cases. And we'll be having n and m. So we want to define some arrays here. We want to make paths of m, which we'll calculate later. I guess that's it. And then we want to make a vector here, which is called P, that will store the prime numbers we will get here. Okay. And then we will take the edges for entitled to xy. I'll subtract x and y by 1 because it's 0-based index. So edge of x, push back y. Then I'll take m, and so I resize b to have size of m. P dot resize to have a size of m, and then loop m times and take p of I. Okay. So that's the input now. So now we want to continue our calculations. So first we will start calculating the value of calc for each node. So we'll just run that DFS from the first node, which is 0. And for the parent, the first node has no parent. So we will give it -1. This should be end, of course. Okay, so the first node has no parent, so we'll give it -1. And then after getting the value for each calc, how can we calculate paths? We will also run another DFS. We can do it iteratively without DFS, but DFS would be easier. Okay. Nodes, again parent. And then we will go through every edge for each child. If child not equals to parent, then I am now at an edge. So I am now looping through every edge from my current node to my child. And then I calculate the number of paths at the edge uh, passing from child to node. Okay, so paths of child, or paths of node. Yes, paths of child. So paths of child means the edge connecting from node to child will be equals to, as I said, nodes of node multiplied by nodes of 0, not 1, because it's 0-based index, minus nodes of nodes. Okay, and of course I want to make this long, because the value would be very large. And then this is to ensure that no overflow happens. So it's one long multiplied by everything. So, and this will be void. Child node if child not equals to parent. And then after that, after calculating the value of the child, we will DFS this child having parent of node. Okay, that's child equal nodes of node multiplied. Wrongly, it shouldn't be nodes of node, nodes of child. Okay, because it's paths of child. And then I'll run the DFS starting from 0 with a parent of -1. So now I have paths array ready. The only left part is the prime numbers. I want to resize it in such a way, as I said, to make its size exactly equals to n-1. Okay. So I'll say while p.size smaller than n minus 1, I just add 1. So p push back 1. Okay, but what if it's greater than n minus 1? So if p dot size greater than n minus 1, so I'll first sort it from in a non-decreasing order, and then multiply the last with the second last, and keep multiplying until its size becomes n minus 1. Okay, so p dot begin, p dot ends, and then while p dot size greater than n minus 1, I multiply the last with the second last. So that means that the value of the second last will be equals to, so p of p dot size minus 2. So this is the index of the second last value, will be equals to the multiplication of the last value, which is p dot back, multiplied by p of p dot size minus 2. Okay, and after that, after I multiplied the last value with the second last value, I'll just remove the last element. So I'll say p dot pop back. That's it. But there is a thing, so I'll talk about it later. Okay. So after I finish that, realize that these values are very large. Okay. So I could have 6 times 10 power 4, 6 times 10 power 4 times, right? So I could make 6 times 10 power 4 power 6 times 10 power 4. So it clearly will not fit any integer type or any data type. Okay, so I should mod in the way. So I should print the answer modded with 10 power 9 plus 7. So I'll mod everything in my way. Okay, so I'll make a separate function to make it easier to multiply by mod and add by mod. So let's say int mul takes a and b, and then it just returns 1 long times a times b mod mod. Of course, I'll make mod equals 29 plus 7. And I'll make an add function that again takes a and b, and it returns a plus b mod mod. Notice I didn't put 1 long here because a plus b won't go out of integer bounds. Okay, it will be small. That's it. So instead of multiplying in that normal way, I'd say that p of p size minus 2 equals the multiplication between these. That's it. And then to get the value, I'll just sort these two and add to the answer. So I'll have an integer answer equals to 0. And I'll sort p again. And then sort paths. Paths. And then paths plus n minus 1. So paths will start. So paths will start from 1 to until 0. Okay, I'll sort the first n values. But I'll have, okay. But there is a thing. So paths of 0, there will be nothing in path of 0 because I'm starting to calculate from paths of 1. I'm not calculating the paths for the first node. So I'll just forget about the first node and start from 1. Okay. So I'll start from 1 here. X smaller than 10 y plus plus. So I'll take the value of the first element in paths, which is located at index 1, but with the value of the first element in P, which is located at index 0, right? So nth equals add nth and the multiplication between paths of I with P of I minus 1. Okay. And then I'll print answer at the end. So first, before every test, I want to reset and empty every array, because at each test I'll have these arrays filled with something from the test before. So I want to empty everything. So I'll just loop for int I equals to 0 and then edge of I dot clear. I'll clear the adjacency list for every node and clear paths. Paths with 0 and size of paths. And I want to clear nodes, but nodes, there is nothing to worry at because nodes are reset every time. Every time nodes are reset, so I don't want to reset it to 0. Okay. Is there anything missing here? Okay, since I'm starting from index number 1, I'll sort starting from paths of 1. I think everything's okay, but let's try. There are some errors. So here I mean adjacent list of nodes. So it's waiting for another input. Oh, I didn't take n. 286. 17, 18, 286. Okay, I think everything is okay now. Of course, because this code is long, feel free to ask at any part you don't understand in this code. Okay. Yes, you might have questions. Okay, I think everything's okay. Let's try submitting. So I should, since mal function takes integers, then I'll cast so paths of I could be long. Then I'll cast it to integer, but first I'll model it with mod. Okay. I hope there is no bug. Oof, there is a bug. There should be a small bug here. Something I didn't notice. So for this loop, I think there's something here. Okay, so I'll look at my last code. It's the same thing. So let's forget about handling cases of +1 and n and so on, and just make this a vector, so it will be easier. That's what I made it in the contest. So paths of m. No, it's just paths. So this is just a vector, and I'll push to it the value of the paths for each edge. Paths to push back this value. Okay, and sure it will be long. And then here sort. Paths to begin. Paths to end. And then here just start from 0. And don't forget to clear paths. So paths dot don't here to long paths. So I'm just paths dot clear. So everything should be okay now. Same thing. Okay, so this is an added test case to handle some cases after the contest. So let's see. 1, 2, 2, 3, 4. So actually what happened here is that this problem I solved in the contest and got accepted, but after the contest they added another case to fail some solutions, so I didn't take care of that case. So if I didn't If I didn't get that corner case now in front of you, I'll sure let you know after we finish. Because that wasn't in consideration at all. So I'll take another 3 minutes to see what's the problem with that case. Then and then leave you if I didn't found it. Okay. Let's see here some explanation. Okay, so since there is a small corner case, I don't know what the problem here, but this idea is the correct idea that gets the full solution. But the corner case here they added so that some solutions have some small part they didn't consider. So I'll let you know after we finish what was the problem there. But anyways, I'll send you this code, and probably after we finish with 2-3 minutes, the I'll send you what was the problem. Okay. So here I'll send it in the chat. Okay. Okay, I sent this solution now. As I said, after we finish 5 minutes, and I'll search about this corner case, and I'll tell you about it. Okay. Anyone have any questions before I leave? Okay. Thank you for joining me. Bye. See you again.